This video is sponsored by EasyEDA Pro. All the projects in this build were designed using EasyEDA's powerful tools, and you can download it for free at easyeda.com. Hello everyone, as shown in the previous video, where we received the PCBs from JLC PCB. Today we'll begin assembling the components onto these boards. If you haven't watched the previous video yet, just click the card that will appear here at the top. This is our main board, the one responsible for all the control functions of the Nail Pro 1 Maxx. Because the PCB uses very small traces and fine-pitch components, as you can see, the assembly requires precision. For that reason, I ordered a stencil to apply the solder paste, ensuring that every component is placed correctly during the mounting process. I skipped the component insertion step because it's not very important at this moment. And here I'm already showing the final result, which came out with a very clean and satisfying finish. All the SMD components were installed, as well as the connectors that link to the other parts of the project. So this is the final look of the main board. Regarding our switching power supply, we noticed that we have a height limitation, since we need to save space inside the micromotor housing. So I decided to use an SMD electrolytic capacitor on the primary side. Because of its final height, being more compact, this type of capacitor was chosen to help reduce the overall size of the design. Now the next step will be to show this board fully assembled. After installing the components on the power supply, the result is extremely satisfying. The final finish came out extremely perfect. A very clean and good-looking result. So this is our switching power supply, the main power source of the project. And we also have the secondary supply, which is responsible for adjusting the other voltages in the system. That one will be shown next. The secondary power board has already been shown and explained in detail earlier. And now it's time to see its final appearance with all the components installed. And this is the final result of the secondary power supply assembly. I've already done the adjustment beforehand and locked the trim pot with resin. Just remembering that we'll have different input voltages and also different output voltages. At the input, we can have anywhere from 17 to 32 volts DC. I need two 12-volt outputs, one for the fan and one for the power button LED. This output will vary between 17 and 32 volts depending on the micromotor model. And if the output is 32 volts, then I also need an auxiliary 5-volt rail for the H-bridge. Up here at this supply point, I need 5 volts for the main board. And these other connectors are for signals. The final finish is excellent and the overall quality is extremely high. For the H-bridge, as I mentioned in the previous video, I kept the same layout used in commercially available modules. But since it's a dual bridge, I connected both inputs and outputs in parallel, so I can drive both sides at the same time, saving on connectors and wiring. The Nail Pro 1 Maxx works at 30 volts, but as you know, there's a 2-volt drop across the H-bridge. So it's powered with 32 volts at the input to get 30 volts at the output. And here we can see how it looks after installing all the components. Very clean and symmetrical. Remember, this is a dedicated layout. Here we have the power connector, with all the information printed on the silkscreen, VCC, GND, and the plus 5V auxiliary if needed. If you're going to use the auxiliary 5 volts, you must remove the jumper on the board. But if the H-bridge supply is below 20 volts, you keep the jumper in place and use the 5 volts provided by the onboard 78M05, which regulates the voltage and powers the H-bridge circuit. And this is the final result of our H-bridge. For my rotary encoder, there wasn't much mystery, just like I mentioned before. It's a simple circuit, but with dedicated pinouts that match directly with the main board. And that's why I made it as a dedicated module. And we also have the small board that provides the backlight for the knob. This board sits between the knob and the rotary encoder, creating the lighting effect for the adjustment button. So now let's take a look at how both boards look once assembled with their components. For my rotary encoder, there wasn't much mystery, just like I mentioned before. It's a simple circuit, but with dedicated pinouts that match directly with the main board. And that's why I made it as a dedicated module. And we also have the small board that provides the backlight for the knob. This board sits between the knob and the rotary encoder, creating the lighting effect for the adjustment button. So now let's take a look at how both boards look once assembled with their components. Now we need to verify that everything is working as expected. Now with the circuit pre-assembled, we already have the OLED display connected, the forward and reverse direction LEDs, the knob LED board, and also the rotary encoder. But it's not working yet because I haven't loaded the firmware to it. So for that, I'm going to upload it using a USB to serial converter that I built myself. I connect it to the main board. And now we can upload the firmware to the board. After the white LEDs flash, the RX and TX LEDs start blinking. And here the magic happens. The KJ Technology logo shows up on the display, and the firmware starts perfectly. Now let's run a few initial tests. We can see everything worked as expected, so we can disconnect the USB serial converter. Let's reset it. And now we're sure the firmware started correctly, showing the greeting messages before going to the speed screen. Now let's test the functions out. The forward LED is on. Let's press the switch to reverse. The LED switched, confirming reverse. Now let's test the speed control. It's going up in 5% steps. It's working correctly. In the firmware, I added profiles so the user can choose the adjustment method they prefer, with options of 5%, 10%, and 20%. To do that, we hold the switch for 5 seconds, and then it goes into the adjustment profile menu. Once we release the switch, the profile menu appears. Let's select the 10% profile. I confirm it on the switch. Profile saved. Loading. And now we have adjustments of 10% at a time. It worked correctly. Now let's choose the 20% adjustment. I hold the switch for 5 seconds. I release the switch to access the profile menu, and now I select the 20% option. Confirm it on the switch. Profile saved. And now we have adjustments of 20% at a time. It works perfectly. And just a reminder, these profile values are saved in the EEPROM, so there's no problem turning the unit off. Everything stays stored until the user selects another profile. Now let's move on to the next step of the project. Now, to test the result of our power supply, we need to check if it really adjusts the voltage through the trim pot. Let's power it from the mains so we can perform this test. Warning! This test was performed in an isolated and controlled environment. Never work on energized equipment without proper knowledge and the necessary safety protection. The power supply is energized. We can see it's already giving us 20 volts. Now let's reduce this voltage. Turning the trim pot counterclockwise makes the voltage go down. We reached 17 volts, which is the minimum voltage we were aiming for. Now I need to test it and see if it can hit 32 volts, which is our target for the maximum output voltage. So now I turn it clockwise to increase the voltage. Because this trim pot is multi-turn, maintaining proper screwdriver alignment is a bit challenging. It's so cool. We hit 33 volts. That's actually above our 32-volt target. But that's exactly what I expected, because this power supply was engineered to deliver a minimum of 16 volts and a maximum of 35 volts. We hit our target, a rock-solid 32 volts, right on the mark. Don't miss the upcoming videos. We're entering the final stretch of this build. Thanks for watching, and I'll see you in the next one.